So this is Physics 2211, problem 3. A block of mass m is suspended motionless by a string and three identical strings as shown in the figure. Each spring has stiffness k and relaxed length L0 or L0. The spring from above forms an angle theta with the horizontal. The string has unknown tension and the Earth's gravity points down. So the question pretty much asks you to determine the tension T in the string right here if the stretch length of the upper string is 3 L0. It will help if you start identifying the forces acting on the system and sketch a corresponding force diagram. So let's start with that, a free body diagram. So if we treat M as our system, we can make a dot for the mass right here. We see that there's a few forces acting on it. There's the force due to gravity acting downward on it. Call that F grav. There's an upward force from the string that we're going to call T. There's a tension. There's a force suspending the mass right here that we can call, we can call that F1. And there's also another force in the, actually, if we label them all in the y direction, if we label it all in the label it all in the y direction, we see that there's another force acting on it. So if I were to just make this bigger, there is the y component of this spring right here that we see. So we could just make a slight slant to it, and we can call this F2. So these are all the forces acting on it. Now the question asks find T, find the value for T. So what we're going to have to do is use our Hooke's law equation, which is F net is equal to K S L hat, where S is equal to L minus L naught. Well, in this case, we say that the stretch length is 3 L naught. So L is equal to 3 L naught. So what we have here is S is equal to 3 L naught minus L naught, which is 2 L naught. So here we go with K 2 L naught L hat is equal to F net. So we have to ask ourselves, what is F net composed of? It's the sum of all the forces acting on our mass. So F net is composed of T plus the X component, a Y component of this spring that was here. So we're going to have to calculate that, and we can do that right now. We can say that if this is our triangle that this spring forms with the mass, this is our angle, and let's say call this X, and let's call this F2, which parallels what we have here, right? Actually, I'm sorry. We call this F2, but we can call this F2X. F2Y. Right. So if this is F2 and this is F2Y, we can say we care about finding this value. So if we want to solve for that, we're going to have to use, let's see, what would we use? What would work best? We could use sine, I believe. Let's try that first. Sine theta is equal to opposite over adjacent, which is f2y over f2. And then you would say f2 sine theta is equal to f2y. I think we can roll with that. Okay. So that's the force of this spring in the y direction. So ft plus f2y, or sorry, f2 sine theta plus f grav plus, actually, should that cover it all? Okay, yeah, so we're only worried about the y direction, so let's do that. Oh, and this should be a minus sign because gravity's working in the opposite negative y direction. It's the positive y direction. So, and that's set that equal to k. This would turn into, sorry, 2k, 2l hat, 2l hat. So, let's see where we're at. All right, we're solving for t. So we're gonna find that t, oh, and we know that we're dealing with the mass m. So we'll say mg here. So we say t is equal to k 2 L naught 2 L naught L hat minus F2 sine theta plus mg. So let's see. Would that get us to where we need to be? Almost. F2 sine theta. Right. Let's see. F2 sine theta is this. F2 is equal to 2y over sine theta. Okay. So oh, actually, you know what? We're only calculating forces in this case. So I guess that's the beauty of learning. We know that since this is an equilibrium, static equilibrium, it's in a certain position and stagnant in a certain position. We know that the sum of all the forces, the net force, is going to be 0 because it's a stationary object in static equilibrium. Because it's being suspended. We're given that in the problem. So we know that F net ultimately is going to be equal to 0. So what's going to prove that? We have T. We have the force in the y direction, the force of the spring in the y direction, which is F2 sine theta plus mg minus mg, oops, is set equal to 0. All right? And we want to, and to make things more clear, we have to define what F2 is. So F2 this value f2 that we labeled here, let's say that's f2, sorry, that f2 here is actually equal to force. So we know by Hooke's law, we know that force is equal to, of a spring, which is what we're dealing with, a spring, is equal to K L minus L naught. And like in what we said, L naught is equal to, L minus L naught would be 3L naught minus L naught, which is 2L naught, sine theta minus mg. So equals to 0. So we'll say that t, since that's what we're looking for, is equal to negative, let's make this cleaner, negative 2k L naught sine theta plus mg. And that's t, what we're trying to calculate. So that was the most challenging part of this problem, part A of problem 3 on Physics 2211, test 2.